Good afternoon, everyone. I'm glad to have the opportunity of making the presentation, and thank you for being here. Today's topic is simplify CDC pipeline with SparkStreaming SQL and data lake. First of all, please allow me to introduce myself. I am a staff engineer from Alibaba Cloud's MapReduce product team. I'm a Spark contributor focused on Spark SQL, and I am also a Hive on Data contributor. My presentation is in 3 parts. Firstly, I'm going to take a look at what is CDC. Secondly, I will propose our CDC solution using SparkStreaming SQL and data lake. And finally, I will introduce some future work. First, let's take a look at what is CDC. If you are a data engineer, you probably have already come across the term CDC. CDC is short for change data capture. It is an approach to data integration that is based on the tracking, capture, and the delivery of the change to data source. In database, CDC can help to load the source table into your data warehouse or data lake. Here is a CDC pipeline for database. There are lots of data stored in the database of application servers, and then we want to analyze this table. It is not probably to run the query against the database directly because it will affect the application performance. So we can use CDC to load the table to the external data warehouse or data lake. After that, we can do ETL or ad hoc on the target table stored in the data warehouse. There are a lot of CDC solutions, including incremental import jobs or a real-time job. Scoop is an open source tool that transfers data between Hadoop and relational database. You can create a daily scheduled Scoop incremental import job to load the data to Hive data warehouse. But Scoop solution have some drawbacks. For example, it still have load pressure on source database, which will affect the application's performance. And the batch job scheduled hourly and daily can't meet the need of real-time analysis. Additionally, Scoop increment solution also have some limitation to the source table, such as it needs a last modified timestamp column. And the Scoop can't handle delete rows because the subsequent increment job only import update or inserted rows newer than rows previously imported. It can't capture the deleted rows. And we should do some DDL on the Hive table manually if the schema of the source table changes. Another solution of CDC is using the binlog of the database. The binlog is a set of sequence log files that contain record of insert, update, delete operations. Here is a streaming CDC pipeline using binlog. First, we can use some open source tools like Databricks, Maxwell to sync binlog to Kafka. After that, SparkStreaming consumes the topic from Kafka sequentially, pass the binlog record, and then write to targeted storage system which support insert, update, delete like kudu or data or HBase. If you want to replace binlog to Hive, you should do more complex merge logic by yourself. This solution also has some drawbacks. For example, HBase and kudu both have heavy servers, and we have lots of operational support. If the data is too large, kudu have some potential scalability problem, and HBase can't support high throughput analytics. We have talked about the above two CDC solutions. One is batch mode using scoop, and another is streaming mode using binlog. But they both have drawbacks. Here, we propose our CDC solution using SparkStreaming SQL and data lake. We can write streaming SQL to pass the binlog and merge them into data lake. Next, I will introduce SparkStreaming SQL first. SQL is a declarative language. Almost all of the data engineers have SQL skills, especially in database and data warehouse, such as MySQL, HiveSQL, SparkSQL, etc. SQL make data analysis more easily and effectively. User can focus on their business logic. There are lots of streaming engines provide SQL language like KSQL, Flink SQL, etc. By using Stream SQL, even if the user are not familiar with SparkStreaming, or the user never learned Java or Scala programming language, they can also easily develop streaming processing. Additionally, it is also low cost if you want to migrate from batch SQL job to streaming SQL job. In Spark's community, there is a related Jira which discusses to support streaming SQL in Spark. And our team also get involved in this SPIP. Furthermore, we have implemented our version of streaming SQL, and we have integrated into our product EMR in Alibaba Cloud. The figure on the left hand shows the streaming SQL operation on the Spark engine stack. It is on the top of structured streaming. We provide some DDL and DML. For DDL, we support create table as select, create scan, and create stream. For DML, we support insert into, merge into. And we also support some other operators like select, where, group by, join, union. And the UDF is also supported. Above all, structured streaming supports lots of sink and source. And we add more sink and source support, such as we support some storage product in Alibaba Cloud, like Log Hub, Tape Store, etc., and others like Kudu or Redis. We introduce some new keywords in DDL and DML. Next, I will pick some of them to explain why need them and how to use them. The first one is create stream. Create stream syntax define how to read a table. Why should we introduce scan to define how to read a table instead of reading the created data source table directly? Because table created by Spark SQL is just a definition of data source. If we support both streaming SQL and batch SQL, Spark can't determine whether this table related SQL is a batch query or a streaming query. So we introduce the create scan syntax. Take Kafka for example. As you know that Kafka data source table can be both used in streaming and batch processing. In batch mode, we can use Spark SQL to query this Kafka data source table directly. But for streaming SQL, we must create a scan to tell the Spark engine that it is a stream type query. Here is the scan detail syntax. Create scan table name alias on a data source table and set the query type by the keyword using. Additionally, we can also set runtime parameters of this scan in option clause, such as max offset per trigger. Create scan is a temporary runtime view on top of the data source table. It is not saved in Hive metastore. It will be deleted after the Spark session exit. Create scan can't be used to define a target table. So if we want to use batch mode, we can query on the data source table directly, or we can create a batch scan on top of the table. If we want to use streaming mode, we must create a stream scan on top of the table. After create a stream scan on top of Kafka data source table, then we can use DML SQL to process the streaming data source. For example, we can select from the data source and insert into the target table like data. But for streaming job, there are lots of runtime job parameters like checkpoint, location, output mode, etc. How should we set these parameters for this job through SQL? Here, we introduce create-stream syntax. A stream represents a struct streaming job. It wraps the job parameters together with DML SQL. Here is the detailed syntax. Create stream Kafka text stream job with options clause, which is used to set the runtime stream job parameters and the DML operations on the Kafka text scan. Additionally, it is allowed to run multiple stream jobs in one application. So we support to create multiple streams in one SQL file. Every create stream has its own job parameters under its own option clause. This is very effective and clearly. Merge into statement is the combination of insert, update, and delete. You can specify a condition to determine whether to update data or insert data to the target table. Here is the merge into syntax. Merge into a target table from the source data defined in the using clause. The source in using clause can be a created stream scan or a subquery. At the end, we should also provide the merge condition to determine whether to do update, delete, insert to the target table. We can use merge into to replace binlog. Currently, we support data and kudu as the target table. This command can simplify the implement of CDC in stream mode. And this is a simple example. UDF is an important part of data analysis. It can extend more ability to process data using SQL. SparkStreaming SQL also supports SparkSQL UDF or Hive UDF. And it also supports some window functions. Window functions support streaming to do aggregation over an event time window. And we support two window types. One is tumbling window, which means all the windows in the stream job are not overlapped. Another one is hopping window or sliding window, which means windows in the streaming job can be overlapped. And watermark is used to resolve the problem of late data. You can define the watermark of a query by specifying the event time column and the threshold on how late the data is expected to be. In DataFrame API, we can use this watermark function to set it. In our stream SQL, we can put a delay UDF in the while statement. Here is an example. Query data from Kafka to do average operator over a tumbling window with a 2 minutes watermark. Till now, I have introduced SparkStreaming SQL We can use SQL to implement a SparkStreaming job instead of Scala or Java API. It is more simple and more effective. Next, I will introduce Data Lake and our work on it. Data Lake is an open source storage layer. Databricks described it as a lakehouse, which is a new data management paradigm. It combines the advantage of data lake and data warehouse. This figure shows the key feature of the data lake. Data lake is built on the Parquet format and provides some features to support more complex data analysis requirements. For example, Data Lake has its own metadata management, which can handle petabyte scale tables with billions of partitions and files at ease. The most important is that it supports ACID transaction. Then we can unify batch and streaming. That is, we can use SparkStreaming to sync data to data table, and at the same time, we can do a batch query on the same table. So it is easy to build a real-time data pipeline. We can also do the update, delete, or merge operation on the data table. Besides, it can support schema enforcement and evaluation, which can provide better data quality and data management. Time travel provides snapshots of data. Then we can query any earlier version of the data. Currently, only Spark can write data to data, including batch mode and streaming mode. And Presto Hive Spark can query data from data. Our team also do lots of improvement of data lake. Firstly, we provide SQL support for some operations of data lake, like update, delete, optimize, and vacuum, etc. And provide streaming SQL related DDL and DML. Additionally, we support Hive and Presto to query data tables, which is different from the implement of data community. For example, once we create a Hive on data table, we can query it by Presto or Hive, but in the community, Presto and Hive both have their own tables. Here is an example to show how we use Presto and Hive to query data table. Above all, I have introduced our work on SparkStreaming, SQL, and Data Lake. Next, I will introduce our CDC solution using SparkStreaming SQL and Data Lake. We can get some benefit from this solution. Firstly, binlog can eliminate the load pressure on the source database. Secondly, Data Lake is just a static jar. It has no extra servers to operate. Thirdly, SparkStreaming SQL can simplify the implement of replacing binlog. There's no need to write Java or Scala code. And last, the CDC pipeline provides low latency data analysis. The channel data on the source table can be synced to Data Lake with minutes latency. And the user can query the target data table immediately. Next, I will show you how we built the CDC pipeline in detail. First of all, we should sync the binlog of the table to Kafka using Debian or other similar products. Different sync tools have different binlog format, so the binlog parser are also different. Then we can use SparkStreaming SQL to consume the binlog from Kafka and pass the binlog to get the row record data and the operation type of this record, like insert, update, or delete. Then we can merge this past record data to data lake. Here is the example to show how to use SparkStreaming SQL to build the pipeline step by step. Step 1, we should create two tables. One is source Kafka table, and another is target data table. Step 2, we create a stream scan on top of the Kafka table and set some parameters in options clause, like starting offset, max offset per trigger. Step 3 is the major logic of the CDC pipeline. We create a stream to wrap the merge into statement and the job parameters. The merge into contain a using clause which define a subquery on the Kafka source table. For example, passing the binlog, and it also specifies the condition to determine whether to insert, update, delete data to the target data table. For example, when the record from the source table has a matched record in the target table, and the operation type is update, then we should update the target table with new record data. Step 4, we can use streaming SQL command to launch the SQL file. This command will launch a young client mode streaming job. After that, we have built a CDC streaming pipeline, and we can query the data table immediately if there are some data change in the source database table. This figure shows the underlying logic of the merge into statement. As you can see, for each batch of the streaming, we call the data's merge function to merge the past binlog record into the target data table. After we launched a CDC stream job, there are some issues which will affect the job long running stability. The first one is how to handle the small files. Because we call data's merge function for each batch, and commonly the batch interval is about 1 or several minutes, then we will get more and more small files after the job run many days. So we must take some action to handle these small files during the job running. For example, we can increase the batch interval to reduce the calling of the data's merge function. And compaction is an important tool to merge the data small files to large. Compaction doesn't change the data, it just changes the data layout. We suppose SparkSQL to run the optimize command to do compaction. Additionally, because data's merge function will launch Spark job to do join, so we can use the adaptive execution mode to reduce the tasks. This can also significantly reduce small files. Next, I will introduce how we do compaction for the long-running stream job. There are two ways to do compaction. We can launch a scheduled compaction batch job, hourly or daily. This job is just a simple optimize SQL command, but when scheduled compaction job run, it may cause the streaming job failed because of the data's transaction commit conflict. Here, the left figure shows the timeline of the transaction commit between the streaming batch and compaction batch job. First, the streaming batch job reads the data table. Then the compaction job do the transaction commit. After that, the streaming batch job will do its own transaction commit. It will check the commit conflict with the formal compaction transaction commit. If the conflict check failed, the streaming job will fail. The right figure shows how data do the logic of transaction commit conflict check. There are 3 conflict types: concurrent append exception, concurrent delete read exception, concurrent delete exception. For example, according to the left figure, the streaming batch job and the compaction job read the same source data files, and the compaction job will delete the source data files and rewrite to new files, but not change the data. If the streaming batch job do the merge logic and also delete the same source data file, this will cause concurrent delete read exception. Because the deleted data by streaming batch job has been rewritten to new files, this data is not really deleted. So to prevent the streaming pipeline failed from transaction commit check, we also do some work on this. One is that we fix a bug that when the streaming batch only contains insert binlog, it should be always succeed to do transaction commit. Another is that we add retry for the failed batch job if the conflict check failed. Another way to do compaction is auto compaction. We put the compaction operations between the streaming batch. There is no conflict because of sequential execution. Currently, we support fail count strategy to determine whether we should do a compaction during the stream running. For example, if we found the fails count is greater than our threshold setting, we will trigger a compaction. The third way to reduce small fails is use adaptive execution. Adaptive execution can automate small partitions to decrease the number of reducers and decrease the number of output fails. Above all, I have introduced the small fails issue and provide some solutions. Next, I will introduce another issue, that is performance issue. Because the implement of data merge, it will launch 2 join jobs to do the merge logic. If the target data table size gets larger, the join operation will take more time. This will decrease the performance and affect the long-running stability. The runtime filter can help to improve the performance of join, especially the streaming batch source data is small. Here is the JIRA we submit. At last, I will introduce the future work of the CDC solution. Once schema change auto-detected, we can auto-detect the schema change and handle the schema during the job running. So there's no need to stop the streaming job to handle it. Another is the performance improvement. We want to implement the read-on-merge feature. We can reduce the merge cost of the write side to prevent the processing time of the batch from increasing. We also want to simplify the user experience by sync statement. We can hide the replay binlog logic. The user just tell us the source binlog format type and the target data table. That's all. Thank you.